Imagine a massive artificial intelligence, like a system that has ingested a huge chunk of the internet, right? And then it gets injected with this microscopic dose of actual quantum computation.
Right.
And suddenly, it's correctly answering complex reasoning questions that it literally failed at just moments before. It sounds like the premise of a science fiction novel, but as of very recently, it's actually a documented reality.
Yeah, it really is. I mean, we are looking at a foundational shift in computational architecture today.
Which is wild to even think about.
Truly. And the specifics are laid out in this May 2026 preprint paper from Multiverse Computing. It's RTL 2605.05914 for those keeping track. And there's also corroborating technical reports from Live Science and IBM.
So we have some really solid sources backing this up.
Exactly. And our goal today is to really strip away all the industry buzzwords. We need to understand the actual physical and mathematical mechanics of, how researchers successfully grafted a real quantum processor onto a classical large language model.
Okay, let's unpack this. Because, classical AI and quantum computers operate on fundamentally incompatible physics.
Oh, completely.
Right. A classical AI processes data using standard digital bits, just zeros and ones. But a quantum computer uses qubits that exist in a state of superposition. They hold multiple probabilities simultaneously. So how do you physically wire a classical system to a quantum system without the AI just, completely breaking down from the incompatible data formats?
Well, the trick is you don't rewrite the classical system to be quantum.
Oh.
Yeah, because current quantum computers simply cannot handle the sheer size of a modern AI. It's impossible right now. So what the researchers did was take a highly capable classical model, in this case, Meta's Llama 3.18b Instruct, and they performed a very highly targeted architectural insertion.
Got it. And the 8B in that name means 8 billion parameters, right? Which are basically the synaptic connections in the model's neural network. Now, the paper notes, they froze those 8 billion parameters. And I understand that freezing a model prevents catastrophic forgetting. You lock the connections in place so the AI doesn't just get lobotomized and forget how to speak English when you introduce new training data.
Right, you have to preserve the base knowledge.
But if the main brain is completely frozen, how does the AI actually incorporate and learn from this new quantum injection?
Because the learning happens exclusively in the new hardware they splice in. So while that massive 8 billion parameter brain was locked down, the researchers inserted these tiny quantum blocks. They're called Cayley parameterized unitary adapters, or CUAs.
Cayley parameterized unitary adapters. Say that 5 times fast.
Right. But they didn't just scatter these adapters randomly. They placed them very specifically inside the transformer's projection layers.
Okay, wait. If we look at how a transformer model reads a sentence, the attention mechanism is what figures out which words matter to each other.
Yeah.
And the projection layer, that's the bottleneck that takes all that complex context and maps it back into the model's main dimensional space. It's where the AI kind of solidifies the high-dimensional relationships between concepts, right?
You nailed it. And that bottleneck is actually the perfect place for a quantum upgrade.
Really? Why there specifically?
Because classical computers really struggle with massive high-dimensional vector spaces. They multiply matrices of numbers to represent data, but as those classical matrices get updated during training, the mathematical geometry can become distorted. Information literally gets lost or compressed inefficiently.
Oh, I see.
But quantum mechanics natively relies on what we call unitary matrices. And a unitary matrix is this beautiful mathematical structure that preserves distances and angles perfectly in a complex vector space.
So if I take a high-resolution JPEG and resize it over and over using classical software, eventually I lose pixel data, right? It gets all blurry. But a unitary matrix operates more like a perfect lossless rotation of a 3D object. You change how you're looking at the data, but the object itself remains mathematically pristine. You don't lose any conceptual resolution.
That is a perfect analogy, and that lossless transformation is incredibly powerful for an AI that's trying to hold on to really nuanced context. And this is there is a massive engineering hurdle here.
There usually is.
Yeah, you cannot train a unitary matrix using standard classical AI training methods.
Because of the backpropagation.
Exactly. Classical AI learns through backpropagation. It calculates errors, updates the numbers, and goes back through the network. But if you use backpropagation on a unitary matrix, it mathematically breaks down. It loses those pristine unitary properties.
It destroys the very thing that makes it useful.
Right.
So the system needs a translator. It needs some way to train the AI using that messy classical backpropagation without destroying the fragile quantum math.
And that translator is the Cayley transform.
Ah, from the name of the adapter.
Yep. It's a mathematical function that takes standard, easily trained classical matrices, specifically skew-symmetric ones, and smoothly maps them into perfect unitary matrices.
Wow.
So the Cayley parameterized unitary adapter lets the classical AI optimize its parameters using the standard methods it already knows, while the actual computation is executed as a flawless quantum operation.
Okay, looking at how this operates physically, an analogy comes to mind. So imagine having a world-class Michelin star chef. That's our classical Llama 3.1 AI.
Okay, I'm with you.
It normally figures out recipe pairings by tasting like 10,000 ingredients sequentially, one after another, trying to map out what works. That's your standard classical processing.
Right.
But the Cayley adapter doesn't teach the chef to cook differently. Instead, you just give them the specialized quantum gadget like a molecular chemical analyzer that instantly maps the overlapping flavor profiles of all 10,000 ingredients simultaneously. It lets them taste flavors in superposition.
That's spot on.
It bypasses the sequential bottleneck entirely and just hands the classical system the fully resolved answer.
And that ability right there to map overlapping possibilities simultaneously, that is the core definition of quantum advantage. The classical model routes a highly complex mathematical request, this high-dimensional projection, straight to the CUA.
And we should clarify for the listener, this wasn't just some software simulation, right?
No, not at all. Once the adapter was trained, the researchers ran the inference on actual quantum hardware, specifically the 156 Qubits R2 processor.
The one inside the IBM Quantum system, too.
Exactly, over in Donostia in the Basque Country.
The physical reality of this is just wild to me. I mean, you have a classical neural network running on standard silicon GPUs, pausing its computation, firing a mathematically translated tensor over an internet connection to a supercooled quantum processor in Spain.
Which is manipulating physical qubits in superposition.
And then firing the result back to the AI just so it can finish a sentence.
Yeah, the latency of that physical trip across the internet is significant right now, obviously. But the architectural proof of concept is what really matters here. A classical system successfully delegated its most complex representational math to a quantum processor and actually understood the answer it got back.
Okay, let's talk about the sheer scale of that delegation, because the ratio of classical to quantum architecture here is kind of jarring.
It really is.
Llama 3.1 has 8 billion parameters. But those Cayley parameterized unitary adapters added a total of roughly 6,000 parameters to the model. We are talking about less than 1 part per million.
Yeah, just 6,000 parameters doing the heavy lifting in an 8 billion parameter system.
So if the AI is a library with 1 million books, they literally added a single paragraph to one page. And yet, that microscopic injection fundamentally changed the AI's reasoning capability.
It did. The multiverse computing team benchmarked this hybrid model against the Wikitext dataset, and they measured a metric called perplexity.
Right, perplexity tracks how confused or uncertain an AI is when it's predicting the next word.
Exactly. So the base classical model scored an 8.877. But the hybrid quantum model dropped that to 8.752.
Which is a 1.4% reduction in perplexity.
Yeah, 1.4%.
Okay, here's where it gets really interesting, and I have to push back here on behalf of anyone listening to this.
Go for it.
A 1.4% improvement sounds utterly insignificant to the average person. Like, if my smartphone battery lasts 1.4% longer, I'm not throwing a parade. If a software update makes my browser 1.4% faster, I won't even notice. Why should you, the listener, care about a 1.4% change on a benchmark chart if you're not a computer scientist?
That is a very fair question. But you have to understand, perplexity is not a linear metric like battery life. It is exponential.
Exponential how?
Well, a language model operates by assigning probabilities to tens of thousands of possible next words all at once. When you reduce perplexity in a highly optimized, state-of-the-art model like Llama 3.1, you aren't just making it slightly faster, you are dramatically sharpening its probability distribution.
It's becoming vastly more certain of the right answer.
Exactly. The paper documented that on specific reasoning tasks, the purely classical model completely failed. It hallucinated totally incorrect answers. But the hybrid model, with just that 1.4% better perplexity, crossed the threshold from hallucination to accuracy. It actually solved the problem correctly.
Wow. So that 1.4% shift is literally the boundary line between the machine guessing wrong and actually knowing the correct answer.
Right. That tiny quantum injection reorganized the high-dimensional space just enough to clear the fog.
That's incredible.
And, the multiverse team anticipated skepticism regarding such a small parameter addition. They knew people would say, oh, it's just a statistical anomaly.
Right, a fluke.
Yeah. So to prove the gain was real, they ran a secondary, highly controlled experiment on a much smaller classical model called small LM2, which only has about 135 million parameters.
Okay, so a much smaller sandbox to play in.
Exactly. And they varied the size of the quantum unitary blocks they injected into this smaller model just to see what would happen.
And you found a scaling law, didn't they?
They did.
The paper notes monoconic improvements, meaning as they increased the quantum capacity, the AI's performance reliably went up. But it wasn't just a smooth upward curve, right?
Yeah.
They hit a mathematical wall and then suddenly broke through it in what physicists call a phase transition.
Yeah, a phase transition. In physics, that's a sudden fundamental shift in a system state. Like water turning into ice the exact millisecond it hits 0 degrees.
Right.
In the small M2 experiment, researchers observed a sharp, abrupt spike in AI performance at a very specific point in the scaling.
So what physically triggers that spike? Like, why does the performance suddenly jump instead of just crawling up gradually?
It basically comes down to a battle between quantum expressivity and quantum noise. You have to remember,
Yeah.
qubits are physical hardware, and right now they are incredibly noisy.
Because they're so sensitive.
Exactly. Any environmental interference degrades their mathematical accuracy. So when the quantum adapter is too small, the inherent background noise of the processor just swallows up the benefit. The errors outweigh the calculations.
So the signal just gets completely drowned out by the static.
Yes. But as you scale up the size of the unitary block, the expressivity, which is the raw capacity of the quantum circuit to represent incredibly complex multidimensional ideas, that increases.
Okay, I see where this is going.
And the phase transition occurs at the exact mathematical threshold where the system's expressivity finally overpowers the hardware's decoherence noise.
Boo.
Right. The signal becomes so dense and robust that it blasts right through the static, resulting in this sudden, dramatic jump in the AI's reasoning capability.
The fact that they can pinpoint that exact mathematical threshold proves this isn't just random noise. But, the mention of noise forces us to look at the massive physical limitations hovering over this entire breakthrough.
Oh, absolutely.
Because we are currently trapped in what's called the NISQ era, right?
Yeah.
Noisy intermediate scale quantum. The qubits inside that Heron processor in Spain are profoundly fragile.
Yeah, decoherence is the greatest enemy of quantum computing right now. A qubit holding a state of superposition can be knocked out of that state by almost anything. A microscopic fluctuation in temperature, a stray cosmic ray, or even just electromagnetic interference from the wiring itself.
A cosmic ray, that's how sensitive it is.
Yeah. And when the qubit collapses, the calculation introduces an error into the AI's neural network.
Which explains why the gains are currently sitting at 1.4% instead of 50%. The quantum adapter is actively fighting its own hardware to deliver those pristine unitary matrices back to the classical AI.
Precisely.
And then there's the whole logistics issue. Processing data on the Heron R2 is remarkably slow and astonishingly expensive compared to just running a standard NVIDIA GPU cluster.
Right. I mean, it is not a commercially viable system today. It is
Yeah.
purely a proof of structural mechanics.
So let me pose a practical pushback here. If I am running a major tech company and I need to scale my AI architecture for millions of users today, this hybrid setup is slower and vastly more expensive than traditional silicon. So won't tech companies just stick to what's cheap and easy? Like, why not just buy 50,000 more classical GPUs and brute force the model to be larger? What is actually going to force the industry to adopt this incredibly fragile quantum framework?
Well, if we connect this to the bigger picture, the tech industry is running face first into an absolute energy wall.
Power consumption.
Yes, we cannot continue to scale classical AI by brute force indefinitely. Training and running these models with hundreds of billions of parameters requires literal gigawatts of electricity.
It's massive. Data centers are already exhausting the local power grids of entire cities.
Exactly. I mean, tech companies are literally looking into building dedicated nuclear reactors just to keep their GPUs running. The classical strategy of just add more processors is hitting a very hard ceiling dictated by thermodynamics and economics.
You can't just make the models bigger forever. The physical power requirements become impossible.
Right. And the multiverse computing paper demonstrates an alternative. extreme computational density.
Hmm.
If you can use just 6,000 quantum parameters to do the representational heavy lifting that would normally require billions of classical parameters, you drastically reduce the footprint of the model.
You get a smarter system that requires a fraction of the power to operate.
Exactly. Long-term, hybrid architecture isn't just an optional luxury. It will likely be the only way to scale AI beyond the physical limits of silicon.
So it's an efficiency play at its core.
Very much so.
But, the paper is careful to note the generalization problem, too. This architecture works beautifully for natural language processing because the projection layers in Llama 3.1 map word relationships. But we don't actually know yet if this translates to, say, computer vision, or autonomous driving, or robotic kinematics.
That's true. Identifying which specific computational tasks possess a genuine quantum advantage is the next major hurdle, because not every algorithm needs to evaluate thousands of overlapping states simultaneously.
Right. Finding the exact bottlenecks in multimodal reasoning, where unitary matrices provide a lossless advantage, that will dictate how this architecture is actually adopted.
But IDM clearly sees this as the inevitable path forward, regardless of the current noise limitations. I mean, their hardware roadmap completely ignores the current bottleneck because they're banking on entirely new architecture over the next few years.
Right, the Heron processor is just a stepping stone.
Exactly. IBM's roadmap leads directly to a system called Starling, which is targeted for 2029. And Starling's entire purpose is to deliver fault-tolerant quantum computing.
And fault-tolerant meaning they crack the decoherence problem.
Yes. By using heavy error correction algorithms, they'll group thousands of unstable physical qubits together to act as one perfectly stable logical qubit. And once fault tolerance is achieved, that background noise we discussed earlier drops to near zero. So the moment a pristine, fault-tolerant quantum computer can seamlessly receive tensors from a classical neural network via a Cayley transform, that 1.4% perplexity drop we see today will scale exponentially.
It's like we are watching the foundation of the next half-century of computing being poured right in front of us.
We really are.
We've crossed the threshold from quantum AI being this speculative sci-fi buzzword to a tangible physical circuit. A massive classical AI literally delegated its most complex reasoning to a quantum processor, utilized 6,000 parameters to navigate a state of superposition, and measurably upgraded its understanding of reality.
It fundamentally reframes the whole technological narrative. I mean, for a decade, the conversation has been framed as a race between classical AI and quantum computers, like which one will win out.
AI versus quantum.
Right. But the multiverse computing architecture proves that the apex of computing is not a competition at all. It is a highly efficient hybrid symphony.
I love that phrase.
Yeah. The classical system provides the structure, the memory, and the interface. And the quantum system provides the infinite dimensional canvas for complex reasoning.
Beautifully said. And as we wrap up this deep dive, I want you, the listener, to consider the philosophical implications of that architecture. We are now successfully teaching classical language models, systems that talk to us, write for us, and help us make decisions to access physical hardware that processes multiple conflicting possibilities simultaneously in a state of superposition.
It's deep stuff.
It really is. So what happens when a future fully scaled quantum AI is asked to solve a deeply complex moral or philosophical dilemma? Will its physical ability to hold multiple conflicting truths at exactly the same time lead to multidimensional answers that our purely classical binary human brains can't even comprehend?
Well, if you change the physical structure of how thought is processed, the nature of the logic itself must inevitably change.
Something to ponder the next time you type a prompt into an AI. Thank you for joining us on this deep dive. Keep asking questions, keep challenging the hype, and above all, keep your curiosity ignited. We'll catch you next time.